Assalamualaikum warahmatullahi wabarakatuh. Welcome to the lecture 2. Today we are going to cover the topic stress and strain. By the end of today's lecture, I hope that everyone will be able to understand and define what is stress and strain and how to utilize the Hooke law to calculate the unknown stresses and strain. And then you will be able to determine the material parameter from a stress strain curve, recognize elastic and plastic component of deformation in a material, and also identify the regions of behavior on the stress strain diagram. Now let us look into the stress and strain one by one. The first one, we will look into the direct stress. So what is direct stress? It is a force that we apply on the elastic body and then it will cause the body to deform. So the way in which the body deform depend on the type of the force that we apply on the object, okay, on the body. So for example, if we use the compression force, it will make the body shorter, meaning the height of the object will be reduced, okay. So because we compress the body. If we use the tensile force, then it will make the body longer, meaning we pull them the body, then it will become elongate. For the type of the stress, the first one is normal stress. Okay, so normal stress usually is the load that perpendicular to the area. For example, if let's say we apply the tensile force, okay, it will act on the opposite part of the material, but it's still perpendicular to the object. Okay, so this is for the F2. If it is compressive, then it will act toward the body, okay, but then it's still perpendicular to the surface area of the body. When the normal stress is perpendicular to the area, shear in the other hand acts parallel to the area, okay, so it is a load that is parallel to the area. If you look into this F1, it can be on this direction, on the other direction, and F2 also, but it is it's parallel to the surface area. Lastly, it is the hydrostatic stress, which is the uniform pressure that act upon the body. Okay, so if you can see in here, so on each side of the body there will be pressure. For tensile and compressive forces, it is called direct forces. So for this stress, the force per unit area is usually used for the calculation, okay. So for example, if you look into the equation here, so this is the stress, so it is a force, amount of force that applied on the area, okay. This is the cross-sectional area of the body that we put the force on, and then the unit for this stress is Pascal, okay. So usually we use the kilopascal, megapascal, and gigapascal, okay. So this is the unit, okay, Newton per meter squared. Now let us move to the direct strain. So in many cases, when we apply the force to the body, it will deform, okay. So this deformation we classify it as X. So in engineering, usually we will change this force into the stress and the deformation into the strain. So by this, we can define strain as the deformation per unit of the original line. Okay, so the symbol used for the direct strain is this one, and it is called epsilon. Okay, so if we want to put it into equation, strain equal to epsilon equal to deformation over the original line. So for the strain, it has no unit because both is length. Okay, so this is considered as ratio. Okay, so for most engineering material, it will not stretch too much. Okay, so if it is stretched too much, it will become damaged, right? So strain value usually is very small figure, so that's why it's usually considered micro strain. Okay, so it can be transformed and used with the 10 minus 6, something like that. Okay, Now let us look into the modulus of elasticity. So modulus of elasticity is define the elastic material. Okay, so usually for the elastic material, it will spring back into shape after the force is applied to it. Okay, so this also obey the Hooke law. So this is the law of spring, which state that deformation is directly proportional to the force. If you look this one, force, okay, so it is proportional, the deformation is proportional to the force. Okay, so F over X equal to stiffness. Stiffness is different from the for each material. So if we use for example aluminium and mild steel, the stiffness of each material will be different. Okay, so we can eliminate the size of when we do the calculation by using the stress and strain instead of the force and also the deformation. So if F and X is referred to the direct stress and strain, then we can make it into equation like this one. So F equal to sigma A, okay, so and then X equal to epsilon L. Hence, if we put it into equation, F over X, meaning the stress over strain, okay, we are going to get this equation. Okay, so then when we put this stress over strain, it will become equation FL over AX. Okay, now the stiffness will be in term of the stress and strain by using this equation. Okay, so this one is called the modulus of elasticity. So then we can calculate it using the equation like this. Okay, so the graph of stress against strain will be straight line with gradient of E. Okay, so the unit of E are the same as the unit of the stress. Now let us look into the stress strain diagram. If you are familiar with this one, this is the one that we use or we see during the tensile test. Okay, so this is the graph for the stress and strain. Okay, so here is the stress and this is the strain. So you will see this is the what we call the point, the line before we reach the yield strength. Okay, so this is what we call as the Young modulus or the modulus of elasticity, which is the slope of this one can considered as the Young modulus. Okay, so then it will become to the come to the yield strength, and after it reach the yield strength, the deformation will start to take place until it reach the ultimate strength, and it will go into necking and in the end fracture. We will look into this part one by one. Okay, now let us look into the first part of the stress strain diagram. Okay, so this is the first part of the stress strain diagram, or we call as the elastic region. Okay, so in this area the curve is usually straight line. Okay, so if you can see here, it is always a straight line. And then the stress is proportional to the strain. So this is the stress and this is the strain. So it is proportional to the strain. So material will be linearly elastic. So meaning that when we put the force on the material, if it is not reached the yield strength yet, when we release the force, it will return to the normal shape. Okay, so for the proportional limit, the upper limit to linear line, and the material still respond elastically. So meaning that as I mentioned, so it will still respond elastically, and the curve tend to bend and flatten out. Okay, so for the elastic limit, upon reach this point, if load is removed, the specimen will still return to the original shape. Next is the yielding strength. So when a slight increase in the stress above the elastic region, okay, so this limit will result in the breakdown of the material. So this one will cause the material to deform permanently. Okay, so this behavior we call it as yielding. So the stress that cause this one is that we call as yield stress or yield point. Okay, so this is where it determine the maximum, the area where the force, how much is the maximum force that we can apply, so that the material will deform or not deform. Okay, so for the plastic deformation, once the yield point is reached, the specimen will elongate. Okay, so this specimen will start elongate when we reach the yield strength point. Okay, so the material in this state will be perfectly plastic. Next is the strain hardening. So when we reach the yield point here, okay, so when the yielding has ended, if we put further load on the body, it will start to resulting the curve to rise. Okay, so this one will start to rise until the ultimate strength. So, and it will become flat when it reach the ultimate stress. Okay, and then when the rise is in the curve, so we call it as the strain hardening region. Okay, so while the specimen is elongating, the cross-sectional area of the body also will start to decrease uniformly. Next, after we reach the ultimate area here, ultimate strength area here, so what happen is the necking will start to take place. Okay, so during this necking part, okay, so the ultimate what we call the cross-sectional area will start to localize the region of the specimen, which caused by the slip plane that form within the material. Okay, so actual strain is produced by the shear strain. So as a result, you will see the necking tend to form on the material. If you can recall on the tensile stress test, okay, so we will see the necking on the sample, on the body, and smaller area can only carry lesser load, hence it will start to curve down. So when it start to curve down, the fracture will take place. Now, when the material is already reached the maximum stress that it can withstand, so then the material will stretch and then will break. Okay, so this is what we call as the rupture strength point over here. Okay, so the absolute limit and this stress level is called ultimate tensile stress. So here is what how does the sample will look like when we perform the tensile test. Okay, so when it is in the region of the elastic, okay, so you can see the material is still in the original form, and then when it reach after the yield point, if you can see the cross-sectional area here will start to decrease, where the material will start to elongate. Okay, so when we already reach after the when we are in the strain hardening region. Okay, so when it reach the ultimate point here, it will start to necking. Okay, so you will start to look this part to appear, and then it will start to fracture. Now let us look into the shear stress. Okay, so what is shear stress? It is shear force usually is applied sideways on the material, what we call as transversely loaded. So if you look into this picture, when a pair of shear cut a material, so if you can see, the material is the force is applied sideways of the material. Okay, like this one. Okay, as for this one, it is from the top, and then you put the force over here, and then the material will break in the middle here. Okay, and then when the material is punched, so if you can see here, when we punch the material, this is the removed material, and it will create the hole in this part. Okay, so the force is applied from the top, and then it will break the material in here. Okay, so then another one is when a beam has a transverse load. So this is a beam, and then we give a force on the beam. Okay, so this is considered as the shear stress also. Now, if you put shear stress in words, it is a force per unit area carrying the load. So, meaning that we can put the equation for the shear stress, what the symbol is tau here. Okay, so as F equal F over A. Okay, F is the load that we apply, and A is the cross sectional area of the body that we put the load on. Okay, so for the sign convention for shear force and stress is based on how it shear the material. Okay, so there are two. One is positive shear and another one is negative shear. So if you look into this one, this one is following the positive the right-handed coordinate system. Okay, so if it's going up here, F is going up, and then on the other hand here is down, then it's considered as positive shear. But if it is down first and then it's going up, then it is considered as negative shear. The next one is shear strain. So what is shear strain? It is the force that causes the material to deform. So the shear strain is defined as the ratio of distance of deform. Okay, so this is the distance of the deform. If you look into the picture here, okay, and then over the height. So this is the height. Okay, so since the angle, usually in deformation, the angle will be very small, so we can assume that shear strain equal to x over L, which is the deformation length here over the L. Then you will get the value for the shear strain. Let us look into the modulus of rigidity. So if we conduct the experiment and measure x for various value of f, okay, so then we will find that the material is elastic. It behaves like the spring. Okay, so like I mentioned previously, it is related to the Hooke law. So so long that we not damage the material by using too much of force, the graph of fx will still be straight, as shown in this picture. Okay, so the gradient of the graph is constant, so f over x will be constant, and is this spring stiffness of the block, it will be expressed as Newton per meter. Okay, now if we divide the f by the area of A and then x by the height, then the relationship will be constant. So if we put it into this equation, f over A over x over L, then we will get the equation FL over AX equal to constant, where the f over A is the stress and x over L is the strain. So then we will get that stress over strain is FL over AX, which is the constant. So this constant will have a special value for each elastic material, and this is considered as the modulus of rigidity. Lastly, it is ultimate shear stress. So when the material is sheared beyond a certain limit and it becomes permanently distorted, uh, it will not spring back to the original state of the material. So the elastic limit has been exceeded. So if the material stress to the limit, so that the part will part into two, so meaning that it will break. Okay, so the ultimate limit has been reached. So the ultimate shear stress has a symbol of tau, and this value is used to calculate the force needed by the shear and the punches. Now let us look into some example. Okay, so for the first one, a metal wire is 2.5 mm diameter and 2 meter long. A force of 12 Newton is applied to it and it stretched 0.3 mm. Assume the material is elastic. Determine the following. So the stress in the wire. First, we have to calculate the cross-sectional area. Okay, so if you can remember, the equation for the stress is sigma equal to F over A. So force we already know. Now we have to calculate the cross-sectional area. So in here, because it is round, so you have to calculate using the round cross-sectional area. So at this point, they get it 4.909 mm squared. So then you will be able to get the value 2.44 Newton per meter mm squared. Okay, so if we convert it into the Pascal, meaning that it has to be converted into meter, then you will get 2.44 megapascal. And then uh, for the second one, the strain in the wire, it is X over L. So X is given 0.3 mm, and then divide by the L, which is 2 meter long, which is 2000 mm. So then you will get the strain as 0.00015. Okay. So here are some questions that you can try on your own. Okay, so the answer is already given there, only the steps you have to look into this. Okay, now for the next example, a steel tensile test specimen has a cross-sectional area of 100 mm squared and a gauge length of 50 mm. The gradient of the elastic section is 410 times 10 power of 3 Newton per mm. Determine the modulus of elasticity. So if we look into the equation of the modulus of elasticity, E equal to the sigma over the epsilon, right? So if we make the equation bigger, so it become F over X times L over A. Okay, so this one, if you remember the equation for the elastic region, it is F over X, right, for the Hooke law. So if you look into this one, meaning that the gradient of the elastic section is 410, this is F over X. So this one we can just put it here, time the L over A. L is given 50, A is the 100 mm squared, then you will get the value for the modulus of elasticity. Here are some more examples. You can look into this example and try to understand the step. It is easy. It is just using the same equation. For example, the sigma equal to F over A, and then the modulus of elasticity, and then the epsilon equal to X over L. Okay, so then you can try to solve some problem that I've already given inside the slide also. Here are the question. Okay, so you can try. I've already put the answer inside there. Try to solve so that you can understand about the stress, strain, and shear by yourself using this equation, this problem. So this one is a question for shear. So calculate the force needed to guillotine a sheet of metal 5 mm thick and 0.8 meter wide, given that the ultimate shear stress is 50 MPa. So the ultimate shear stress is already given 50 MPa, and then what we need is to calculate the force needed to guillotine the sheet. Okay, so the area to be cut is, if we can look into the equation, uh, the tau equal to F over A, right? So now you have to calculate the value of A in order to get the value of F, since the tau is already given 50 MPa. So you calculate the value of the A, and then you'll get 4000 meters squared. And then when we put it into the equation, F, it will become F equal to tau times A. Okay, tau is already given 50 MPa time the 4000, then you will get 200,000 Newton or 200 kilonewton. Okay. This one also, the example is quite the same also, only that this is for force needed to punch a hole. Okay, so but the step is still the same, using the tau equal to F over A. Okay, so tau is given 60 MPa. You have to calculate the A, and then when you put it together, you will get this value. And this question still the same for the shear. Okay, so but different condition, which is shear a pin. Okay, so you can find the value of A, and then you put the tau equal to 60 times the area, and then you will get the value 3060 Newton. Okay. And here are some questions that you can try by yourself. Okay, so the answer is already given here. you just need to see what is the steps to calculate this. Okay. In here also I put some link to the videos that can help you to understand more on the stress and strain and also the properties of the material. Okay, so in the next class we are going to go into the bulk deformation processes. Okay, so that make sure that you understand about the stress and strain, because there are a lot of equation inside the process that will require you to use this stress strain equation. Okay, that's the end of lecture 2 on stress and strain. So if you have any question or you are not able to understand about this stress strain lecture, please make sure you contact me. Inshallah, I will try to help you as much as I can. So if you need a synchronous class, I can arrange for the synchronous class next week or so. Okay, so we are going to go into the bulk deformation process, so make sure that you understand on this stress strain before we go into that section. Okay, thank you very much for listening. Assalamualaikum.